I will be talking about climate network modeling and analysis. So far in this conference or in this meetup, you have learned all about what is climate networks, how to form them, in which phenomenon are studied using this climate network. So this is the outline of my talk. This is going to be a very pedagogical talk. In the end, I will talk about my work and we'll talk about the result and we'll discuss about the plots and uh, results. So first I will talk about climate networks, how to construct them, which data set one can use, where one can find them. Then what is the percolation framework, which is usually applied to find construct a climate network based on a correlation function. So then, since it's a correlation network, I will talk about correlation networks. In this case, we have used a linear correlation function, that is we have calculated Pearson correlation function. So I will talk about that. Then I will talk about once you have constructed the network, now you will find the different network characterizers and find the structural changes in those network characterizers. And the whole jargon of doing this is somehow to implement it or to apply it in order to predict various climate phenomenon or in order to understand various climate phenomenon. There are various models which are available, which follow the dynamics, which do the forecast. The network analysis is sort of a bigger picture in which instead of going into the various complicated uh, motions or various complicated models, how we can simplify the things, how we can infer from the huge amount of data which is available to us, how we can make sense of it, and in the end, how to apply it to the real system and how to predict various the last part which I'm going to talk about is I've implemented this climate network framework and I have tried to predict various precursors for the El Nino event or for the tropical cyclone. So to do everything is in order to understand the real system, in order to understand the what is going on in the actual climate system and how we can correlate different nodes based on the real activity which is happening at that nodes. So let's start. So what we have various massive data sets available of precipitation, humidity at various level. We have temperature, near surface temperature, sea surface temperature data is available. We have wind data, wind velocity, which is available by this National Center of Environmental Prediction, National Center of Atmospheric Research, US-based organization, then European Center for mid-range weather forecast, and this Japanese reanalysis data set. So they have this reanalysis data set which give a comprehensive picture of a data or the observation taken at that data point. So they use various forecast models and they do the data assimilation and then they construct a data set which is based, that's why it is called as reanalysis data sets. So we are going to use that in order to construct a climate network. This climate network can be used to forecast some important climatic phenomena such as monsoon, which we have seen in the talk of Elena. She tried to predict the tipping elements and she tried to predict the onset of the monsoon and withdrawal of the monsoon. The North Atlantic oscillation, the El Nino events, which I'm going to talk about in the detail, and the cyclone, for which these two problems I will talk at the end. Once we constructed all the framework, we will see how to implement this. And the percolation framework is used to study the cluster structure. So based once you construct a correlation network, we we use the percolation framework to understand various changes, global structural changes occurring in that climate network, and we try to find out certain precursors, certain measures which are different for the indicator here, which are different in the when the activity is happening, and that way we can use it in a way actually apply this climate network for the real phenomenon. So these are certain papers which have implemented it. You can see the Havlin group. You can also see the Elena's group is there, and our two papers are also there. So, which talk about monsoon. Then there is this Hood's paper, which talk about the representation of wind flows, and we talk about El Nino and tropical cyclones. So let's start from the beginning. So now we have nodes at various points because we have this data set. So for our case, for my case, I have taken the European Center for Middle Range Weather Forecast reanalysis data set of near atmospheric temperature, which is at 1000 hectopascal. So it is at 1 atmospheric pressure. So which is very near to the sea surface. So we want to construct a grid. So now, depending on the activity which or the phenomenon which you're going to study, you decide the resolution. For example, the cyclone, which is slightly localized, you need a finer grid. But for El Nino, you don't need much finer grid. So for this, we have chosen a 7.5 degree resolution for the El Nino grid. So, and you want to construct a uniform grid. So how you will construct, let's say you have some resolution R0. So if you have some resolution R0, so you will calculate the nodes on the equator, which is given by N0 is given by 360 divided by R0. Now, let's say you want to calculate number of nodes on particular latitude, which is separated, which is equidistance in a resolution that is R0. So you want to calculate certain number of nodes on, let's say, MR0 latitude, let's say NM is the number of nodes, which is on MR0 latitude, and that is given by a simple circular function that is cos MR0, whether M goes from minus 90 R0 to 90 R0. In order to get a uniform, so it goes from minus 90 to 90. So we get the total number of nodes as N as summation of M0 to M90 by R0 to NM, that is number on the latitude, minus N0, which is the number of nodes on the equator, because it gets counted twice, so you have to subtract one time. So this is how you connect using Gephi or using Python or using various plotting packages. You can give the resolution for your system depending on which phenomenon you are considering. So for El Nino, we have considered 7.5 degrees of resolution, which is nothing but 830 kilometers. And we have taken the data of sea surface temperature at, near air surface temperature at 1000 hectopascal height at each grid point. Now we have a grid. Now we want to add the links. So how I will add the links? I will calculate the correlation function. I will calculate the Pearson correlation function between the two nodes. Since for each node I have a time series, I have a temperature data of each day. So I have taken, let's say for El Nino, I have taken daily near air surface. So for each day I have one data point. So like that, for each node I have a time series. So I will calculate the Pearson correlation and I will add link. So now, after adding links, what I will do is I will apply the percolation framework. So what is percolation? A system is considered percolating if there is a path from one side of the lattice passing along the bonds or the edges through the occupied vertices or through the occupied links to the other side of the lattice. So now here you can see the system is percolating because you can see the cluster which is going from one side of the lattice to the other side of the lattice. So that's how you define the
You take this, not previous, yeah. So you're taking the whole grid.
Yeah.
And what are you computing the correlation between?
correlation between nodes. I will come to that. I will come to that. I will.
Temperature, that's.
Yeah, temperature. That's the variable. Near air surface temperature at 1000 hectopascal and the daily air so for each day I have one temperature. This is a general picture I'm saying. When I will go to a particular problem, I will give you the time data, I will give you the resolution, I will give the what are the parameters for the Pearson correlation. So that we will talk. This is very pedagogical view of how you construct a climate network based on a data. So percolation theory. So each side of a very large lattice is occupied randomly. So you have a general idea about percolation theory. So when you say that the network is percolating when there is a percolating cluster present at in the lattice at particular, if it is at the probability is rho c at which the percolation happens, that means the lattice is percolating or percolating cluster is formed, then that is known as the order parameter, and it has been applied to many fields: mathematical modeling, epidemiology, social networks, and also in cognitive science. So once you So I was talking about a correlation network. So you calculate a Pearson correlation, which gives the similarity between two variables. It measures the linear correlation between the two variables or the sets of data at two different nodes. So Pearson correlation coefficient is the covariance of the variable divided by the product of the standard deviation. This thing, it does not include yet the time lag, but we will when we will apply it to, let's say, El Nino or the cyclone, we will have much different, similar in the sense of a framework, but more niche equation for the correlation function. So let me show you how. So if you have 4 node points and if you want to, if you, let's say these are the 4 nodes I have. So basically, while constructing a climate network, you're dealing with big, huge CSV file, comma separated variables. So you have certain nodes at, so you have temperature at Jan 1, 2, 3, 4, like 4, and then you have this kind of so you construct a CSV file, which is a SST CSV, and then there are in Python there is this inbuilt command for the calculating correlation matrix. You use that and you get a correlation function. So here you see that the diagonal elements are 1, the matrix is symmetric, which you kind of expect because the self correlation has to be 1. The matrix has to be symmetric because we haven't introduced any directionality into it. So that's the basic or very idea of the calculating a Pearson correlation. So now you know, you have a grid, you know the percolation framework, you have calculated the correlation, you have added the links. Now, once you have the network constructed, how to characterize it, how to see the changes, how to find different measures which we will actually apply to find the differences or find the indicator and when the phenomenon is taking place, which are which we can use as a precursors for the upcoming climatic phenomenon. So here you can see you can calculate the node degree. It is nothing but the number of links that are connected to a node. The degree distribution, so you will get different, every node will have some different node degree. So the distribution, you will find out the total number of links, the betweenness centrality. So if the value of the betweenness centrality of the node, it reflects how important that node is. So this is a basic example of, let's say if you have this kind of network, so the number represents the node degree, and from which you can calculate the total number of nodes, the distribution of these degrees of nodes, and also calculate the betweenness centrality. So now we have the entire framework. We have slight idea of how to construct a climate network from the data set. Now we are going to implement it to a real problem. So let's start with the El Nino phenomenon. What is El Nino phenomenon? It occurs in the Pacific Ocean. What happens is in a normal year, the hot water is is at the western Pacific Ocean, and the eastern Pacific Ocean is slightly colder. But in the El Nino year, that hot water, so there is a thermocline that is nothing but the line drawn at the constant temperature 20 degrees Celsius, so which is slightly tilted uh, in the normal year. But in the El Nino year, it flattens because this water flows towards its eastward, and easterly wind, they weaken. So you have a higher degree, higher SST temperature in the El Nino basin, and which is there is a standard method to quantize this anomaly in the SST, which is the El Nino index. So that is El Nino. It occurs every 2 to 7 years, and you can see this is the Nino index, which we have calculated from 79 to 19. So for each year, we have calculated the 3-month Nino region averages, and we can see that it follows certain oscillation, and based on the whether the SST anomaly is between 0.5 to if it is greater than 0.5, then we say it's weak. If it's between 0.5 to 1. No, if it is 0.5 to, let's see. Yeah, if it is between 0.5 to 0.9 degrees Celsius, temperature SST anomaly is high, 0.5 to 0.9 degrees Celsius, we say it's weak. 1 to 1.4 we say moderate, 1.5 to 2 we say strong El Nino episode, and if its SST anomaly is more than 2 degree higher, then we say very strong. Similar classification can be seen for the El Nino also. So it is very important to predict the El Nino before, and in order to mitigate or in order to do various rescue work. So because it has various global impact on a global climate. So disasters, flooding in the countries like Peru and Ecuador, and you see it is related to droughts in large areas of South America, and it is also very much connected to the Indian monsoon, which we can clearly see in this slide. So this is the rainfall anomaly, which is this slide is taken from this IITM thing. So as you can see, the blue dots, they represents the La Nina activity. These dots, they represents the El Nino activity, and red lines, they show the drought-like condition when the rainfall is quite small. The blue line shows the flood-like condition when the rainfall anomaly is quite high, and green line shows the normal. So you can clearly see that there is a connection between La Nina and the flood-like condition, and El Nino and the drought-like condition. So that can be clearly. So it is important to study the El Nino phenomenon to identify certain precursors in order to predict the El Nino. So now we have, now let's go to the problem in which I will talk about how I have constructed a network in order to construct certain precursors for the El Nino. So here I have taken the data of daily near surface temperature at 1000 hectopascal, and within the period of this from the ECM European Center for Mid-Range Weather Forecast reanalysis data set. And here for each day, I have calculated mean and divided it by the standard deviation. So I have 39 years of data, so I will take a mean over 39 years for each day. So for 1st January, I have 39 points of 1st January. So I will take a mean over that, and I will divide by the standard deviation of that. And then I will calculate the correlation function. The parameters of this are taken from this paper So the averages are taken over year. I and J denotes different nodes. Y indicates the year. So for each year, we construct a network. So we have 39 networks, and let's say for this is the IJ, and we calculate that we have taken the time lag between 0 to 200 days. Ambika has talked about how to choose a time lag value. I will not go into the details. So you have so we have taken time lag to 0 to 200, and we have calculated for each tau the I and j, and then we have taken the maximum value for of correlation for the tau. That value of correlation strength we have taken. So once you have calculated that for various I and j pair, you start adding links. So this is this is how the 7.5 degree resolution looks like. I have 726 nodes, and I will start adding links from higher correlation value to lower correlation value. So this is these are the links which you see in for 0.7 correlation. And while I'm changing the C value, I will calculate a normalized largest cluster and a susceptibility. What is that? I will explain it in the next slide. But here I'm showing you the how we construct a network for each year by adding first the highest correlation link and then going to the lower values. So this is how the network looks for C is equal to 0.65. This is how it looks for 0.5, and this is how it looks for 0.45. So for each C value, once you're constructing the network, you calculate these two quantities, that is normalized largest cluster. So what is normalized largest cluster? Let's say for particular C value, you have a certain cluster. So there is one largest cluster. So you count the number of nodes in that largest cluster and divide it by the total number of nodes. So for El Nino, we have taken El Nino, it is n is equal to 726 nodes. Then you calculate the susceptibility. Now this susceptibility excludes the largest nodes. It looks at the distribution of various smaller networks happening at that particular C. So this summation excludes the largest nodes, and then we calculate, let's say, how many clusters are there with 2 nodes, how many clusters are there with 3 nodes, and we take a summation over that, and we calculate the susceptibility at each C value. Okay, and now we plot these 2 points with respect to the correlation strength. So this is the result and discussion. So we have based this entire constructed this entire correlation function in order to construct certain characterizers, certain precursors to predict which are different for the indicator years and which are different for the El Nino years. So this blue line shows the S1 normalized largest cluster, which goes from 1 to 0, and this green line shows the variance of so it shows the susceptibility. So you can see that this plot is for the December 2013, which precedes the strong El Nino episode. That means this is the indicator year kind of network. So for indicator year network, when you do this plot of C, normalized largest cluster and susceptibility with respect to C, and for strong El Nino episode, when there was very strong El Nino episode, you do the similar plot, you see that susceptibility pattern is quite different. You also see the scale is quite different. For the indicator year, it goes up to 150, and for the El Nino years, it's not that high. And also you can you can use these differences in and formulate certain precursors to so we will see the similar kind of thing for the El Nino episode, which was a strong El Nino episode, and this is the moderate El Nino episode. Again, this yeah. So S is the number of
connections, are they changing with time?
Uh, No, I have taken averages, right? So for every year, I have one network. So I have taken, yeah, so for each year, I have network. They are changing with C, the correlation strength. Since you take the average, you don't.
The largest cluster is the cluster, all those nodes connected. You just measure the length of it. How many nodes are, that's what.
Yeah, how many nodes are in the largest cluster? Yes.
What is this?
Susceptibility is telling us apart from the largest cluster, how many clusters are there in the networks? How many?
The variation,
Yeah, how many?
standard deviation of the variation.
Yeah. So as we see, we can clearly see the distinct pattern before the indicator year and during the El Nino year. So this is for.
Where is the lead?
So, as I mentioned, we have, for each year we have network. So for each year we have these plots. So this is 2013 and this is 2015. So based on 2013 network, I get this plot. Based on 2015 network, I get this plot. And the 2015 is when the very strong El Nino episode happens. And in 2013, there was no El Nino episode. It was preceding the El Nino episode. So you can see the differences in the scale. Susceptibility is quite high. And it is consistent for the other episodes also. Like for 19, this is the indicator years. The indicator years is anything which follows the climatic phenomenon.
Typically, you can predict El Nino 9 months in advance. That was the earliest. Now, here, it's a question of, in El Nino, it's a question of is the El Nino coming or not? Okay. If you can say this, the year before the El Nino comes is pretty important. So here you see one indicator year, and there you see the next year is actually the El Nino. You can see that the indicator years themselves has certain signatures in the susceptibility as well as in the order parameter. And in fact, the most important feature which you see is that you see a jump in the change in susceptibility. It's a very strong jump.
So
that really means one full year before the El Nino comes.
So then if you plot this before 1990, how would that look?
uh,
Would the curve look very different, the green one?
yeah,
Even the previous slide, the slide, they look very similar.
Because here all the years are indicator years and the El Nino.
yeah, I will show you the for yeah. So there is a 2 years difference between this is 2013-15 and in the next slide we will see this 93 and 94. Why it is like that? Because certain episodes started like this episode started in the 2014 itself and it peaked in the 2015. So we have taken the indicator year as 2013, whereas this moderate El Nino it started in 1994. So if you look.
The calendar year. That makes it easy. Okay. And the calendar year itself shows the change. Because if you start moving, the first date, the last date, and so on, you may get better indicators, but it becomes that much harder to do.
But the change, as she said, is primarily scale.
Scale and the pattern also. Yeah, it is very little, but still we can do that. Multiple peaks are observed in the susceptibility. It is.
What is the phenomenon shows is what is the pattern, etc. And it is a feature which varies from there.
So now we have, since now we see that the susceptibility is quite distinct for the indicator year, and it is quite, the pattern is also different for the El Nino years, and the scale is also different for the, so we thought we can use it as a precursor for the susceptibility jump. So here I have given the susceptibility jump for every year from not just indicator and El Nino, we have given it for every year from 1980 to 2018. So we say that when the susceptibility jump or the mod of delta chi, it goes beyond certain threshold, which is 7. This 7 we got by optimizing the false and false alarm and getting better prediction. So when we do that, we see that for indicator years, which are marked by the green arrows, the value of delta chi is quite high. And that's, so if you consider all the activities, there have been 13 El Nino episodes. So this color gradation is according to the strength of the El Nino. So 82, 97 and 2015, very strong El Nino years. 97, 87 and 91 are strong and likewise. So we observe one false alarm in the year of 2000. We think that it is because there was this prolonged La Nina was happening during that time. I guess it was for 32 months of La Nina was happening from July to 98 to February 2001. So yeah, we have a missed prediction and one false alarm and two for missed prediction, but mostly we were able to predict not just the El Nino year, which is coming in the next year. So the susceptibility of the network gives a measure of the variation in the spread of the clusters of different sizes in for a given correlation strength. It is a more definitive and reliable precursor for the upcoming El Nino episode, as not only the this value is significant, but also the sequence of peak or the pattern has is a distinct.
See. Get this. So here from here, right? And a quick look. Can I see the El Nino years there? You said like 30.
Yeah.
Indicate El Nino
So
years.
these red lines are the El Nino years.
So multiple reds.
Yeah, multiple reds.
Are they the light red?
No, the gradation is, all the red lines are El Nino years. The gradation is according, if it is darker shade of red, then that means the episode is very strong. If these are weak episodes. This black is the indicator year which is crossing. This is
So
not
black
all the
lines which cross the
threshold. So these are the indicator years, the which are coming just before.
Can we go again the previous one example? Your susceptibility jump is the jump in that increment. Is that correct?
Yeah, it is a fall, actually the fall, because since we are going from this side.
Anyway, any one of them.
Yeah, okay, so here it will be from this.
Ability jump is okay. Yeah, that is the
Yeah,
jump.
yeah, so
So,
largest jump
The
here it
great,
is.
first point is the largest susceptibility.
And you're setting that here.
Just show the point. Anyway, either way.
The criterion is based on the magnitude of the jump.
That is the strongest indicator. See, you get a prediction based on the susceptibility and the order parameter also. They did, but the susceptibility, but that gives more false positives than this one. This eliminates practically all the false. So that's statistics. To tell them which are the false positives, which are eliminated.
So we get the one false positive here. To show that the eliminated, I have to show the other plot, which is with this. No, so this is the false alarm. These are the correct predictions which are done by that. So in order to summarize that, yeah. So I will. Yeah, I will. So as I talked, it has distinctive pattern, and the crosses the threshold, which we have kept it 7 here. The Eleanor, yeah, that's what. So
How many years? No, 13 out of.
yeah, so the threshold succeed in prediction of 7 events correctly out of 13 with just one false alarm.
Yeah, so show that on the.
So yeah, 1, 2, 3, 4, 5, 6. And some of them are happening side by side. So like 2 years are consecutive. So yeah, we can say that it
Do
is
you have
possible.
speculation on why this jump that didn't happen? Why did that false alarm?
Yeah, as I said that there was prolonged La Nina happening at that time. So maybe because of that, there was some sort of strong correlation happening.
Mother way.
It's a complicated thing, and also how long it lasts. Some of the El Niños actually last.
Yeah, so I will summarize it in the table. You can see the, no, it's in the end, but I will summarize the whole result in the.
Yeah, the thing, wherever there's a El Niño and a La Nina, this is your prediction. Some years there's a El Niño and there's also a La Nina, or very soon after there's.
Yeah, soon
there's
after there is a
Nina.
La
So
Nina.
in those years, your predictions are not so reliable. It's a temperature pattern, right? So, and so many factors influence your temperature pattern.
Also this network thing, right? When you that framework, you have a cluster, right? It seems to be coupling a lot more during these events. Are there more couplings or decouplings? Right? The clusters, you have these clusters
I think,
in the network, right?
Yeah.
So what is telling us about the structure of this thing? Can you infer something physical from this?
yeah, we can.
She's telling you. Going next slide.
Okay.
Next slide. Where you actually had the.
So we will do the topological analysis in order to find certain more precursors which we can club together. We now have the jump in the susceptibility, but we want some more precursors. So together we can minimize the false alarm and we can predict more activities. So this is the histogram. This is the length of teleconnections and the number of links. This is for El Nino 1996. That is before 1 year before the strong El Nino episode, and this is during the very strong El Nino episode. And we can also see in the inset there is this La Nina. So before very strong. The inset shows the 1 year before strong La Nina and during the La Nina. So this is El Nino, El Nino.
Was very, many more long range study.
Yeah, you can see that. And number of connections are quite. So the for indicator years, the connections. Yeah. So the number of links are quite high. So I will summarize this in the, so number of large distance links and or teleconnection links significantly during El Nino as well as La Nina activity, and an increased number of teleconnections with higher value of correlation strength is also seen in the El Nino years, which we can see from this plot. So the total number of links are plotted according to the strength of the correlation. So yeah, so that's the, so if you look at this plot, you see higher number of large teleconnections are seen in the El Nino network as well as in the La Nina network. Yeah, but
See your x-axis. The x-axis. Connections are much, much long.
yeah,
There are people who say it's a small world thing in the El Nino years. The network decouples from the outside in the El Nino years. And then there is speculation as to small world, not small world. About small world, not small world, we can't say. There's no particular. But on the other hand, it is true that the typical teleconnection length smaller than the and it is larger, but it's quite large.
So increased number of tele. So increased number of teleconnections with higher value of correlation are also seen. So you observe much highly correlated links in the El Nino years. The correlation value goes up to 0.9. So this is during very strong El Nino episode. This is 1997, and this is the indicator year 1996. And you see the number of links, the scale, it is somewhere around 7,000 or something, and it is the total number of links are quite high, and you also see the highly correlated links. So these things can also be used as a precursors for the El Nino. Now we are going to do the degree distribution. This is the El Nino basin. So 1 year before very strong El Nino episode, this 1996, during very strong El Nino episode, and these are the teleconnection plots. So you mostly have links in this hemisphere and this hemisphere. There are some spurious links which are crossing, but mainly the contributing links for the degrees are coming. So it is passing the test that the link should not cross across the hemisphere. So and you can clearly see the higher nodes degree, higher nodes with higher degrees are observed in the El Nino basin, which is clearly seen in the El Nino year this year. This is for the indicator year. So we can summarize this in a table and we can calculate. So the for indicator year, the value of CC at which the percolating cluster takes place, the critical correlation value at which the jump in the order parameter takes place is between this value. And for El Nino episode, it's quite higher. Mod of delta chi is ranging between 40 to 100 for indicator years compared to other years. During very strong El Nino activity, the nodes from the El Nino basin have higher degree, which is kind of expected, and they are strongly connected. For indicator years, nodes have lower degree distribution, and you don't find highly connected nodes in the El Nino basin. They appear outside the El Nino basin. So if we look at this figure, so the higher you don't see any nodes for the indicator years, but in the El Nino years you do see. With the degree scale is also quite different. So you can summarize this. So you have constructed 39 networks. So you can summarize this for all the. So these are indicator years, and this is 15 months. So how long that El Nino episode was? 15 months, 18 months, 14 months, like that. And we have made a prediction for each year. We have constructed a network, and we have made a prediction on 31st of December of that year, that whether next year is going to be El Nino. So depending on these parameters, even if you missed the upcoming El Nino episode in the delta chi, there is, you can you can consider the degree distribution and the total number of links, which are also more reliable together to predict the.
The other hand, years you miss it altogether, they are. Okay.
Yeah.
Whenever there's a false positive, if you start looking at the other indicators, or you don't see an El Nino, where because other parameters are there, if you look at the other ones, you can see that yes, something is going to happen.
More reliable in the case of CC and Cmax. I was talking about, but delta chi is the best. And so we have made a prediction on 31st of December for each. So the lead time which we get between the prediction and the beginning of the El Nino episode is 6.4 months. And we predicted before the El Nino episode peaks, that is 11.4 months when we take averages over there. We find the indicator value various. So we can find very certain threshold for the indicator years, and which differentiate between the indicator year and the El Nino years. For the CC, the total number of links, which is around, for indicator years, it is around 10,000. If it is crossing that, if the total number of links are quite high, then we can say the El Nino episode is taking place or it's going to take place. We use this crucial predictor, this jump of susceptibility, the total number of links, and the degree of nodes. And these precursors, these three precursors together identify 10 out of 13 El Nino episodes occurring in the period of this and one false alarm occurring in the period of 39 years. So that was what we did for the El Nino years. Now we will go to the tropical cyclone part. Tropical cyclone, we have applied this mechanism since it to predict or find certain precursors of tropical cyclone. So tropical cyclone is nothing but a large scale air mass which in spiraling, rotating around a center of low atmospheric pressure, and it originate over warm tropical ocean. And we are considering mostly Indian, the Bay of Bengal and Arabian Sea in our grid. So our grid is quite different. It's not global. Our resolution is quite different, and our correlation parameters are also different because since we are considering tropical cyclone. So pre-monsoon, there are bimodal tropical cyclone season. We have studied mostly the post-monsoon cyclone season because maximum tropical frequencies observed in those season. And as we know, it is very important to find certain precursors to predict this tropical cyclone because that way it will help to mitigate the. So we are going to construct a precursors for cyclone by implementing this network frame. We have used the reanalysis data set near surface air temperature for the period of 2013 to 2018. So we will take the averages. Yeah, we tried. We wanted to.
There are certain features which we have identified.
Yeah, but that's what was our aim. So, and we have for El Nino, we have constructed a network for each year. Here we have constructed a network for 15 days. And with 0 to 7 days of time lag, in the El Nino it was 0 to 200. And we have taken this grid size with this resolution, which is around 83 kilometer. For El Nino, it was 830 kilometers. And we again do the formula is same for the normalized largest cluster and the susceptibility, and we try to see the different features which we can see if there are certain signature features for the upcoming cyclone. So this is for cyclone Kant, which happened in the Bay of Bengal from 21st of October to 28th of October. So this is 15 days of network. So this is 16 to 31st of October. For that network, we have calculated the normalized largest cluster, and the blue line is the susceptibility. And for the 1st of 15 October, which is the preceding network just before the cyclone, 15 days of network, we have calculated the S1 and chi, and we can see again, though it is different for El Nino, for indicator years, you got the higher value in the susceptibility, and the pattern was seen before for the indicator years. But in the cyclone, you actually see the higher value of susceptibility in the cyclone when the cyclone was taking place, and the scale is also quite different for before network 15 days network before the cyclone and 15 days network during the cyclone. So this is for cyclone Kant. Uh, uh, this is for cyclone Nada. So again, it was from 29 to 2nd December. So there is no shadow of the cyclone in the first 15 November of network. So you see the scale difference. Again, there is a scale difference. Now the scale is quite high, 400, because Just after 4 days, it was followed by a very strong cyclone, which is Varda. So you can actually see the indicator of that, or certain distinct feature of that in this network, which was which was during 16th and 30th of November in this plot. So the scale is quite high. So the Varda was 6 to 18 December. So here the binning is, what we have done is first to 15 December and 16 to 31st December. We will be able to see the distinction if we do the binning just before the cyclone and during the cyclone. There is no kind of overlap. So here you can see the cyclone because it is 6 to 18. So you can see certain effects in both the plots because there are overlapping three cyclones in the 3 months. So you see the overlapping cyclones. So this is for the Oki. It happened in 2017, 29 to 6 December. So again, the scale is quite different, but again, since it started on 29th and the first network has the 29th date, so this is the susceptibility and the largest cluster plot for network. So now you do the susceptibility jump analysis. So this is how many networks are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 networks are there. For each network is of 15 days, and for each network you calculate the delta chi as a precursors, and you see that so the maximum jump in the susceptibility is plotted for each network. The jump in the cyclone networks, including the overlaps, because there were certain overlaps. One cyclone was followed by another cyclone just in 4 days. And the strength of the cyclone is again shown. So all these reds are the cyclone lines, and the gradation shows the strength of the cyclone. So we know that these are the networks for which there was no overlap in the cyclone. Like in that 15 days, there was no cyclone. So that and for during the cyclone, we see the higher value of susceptibility jump. Here we have done it for Asoba also. Asoba, which was in Arabian Sea. So 15 May is the indicator. This is the Asoba cyclone. Then this is Kant. This is Nada. This is Varada. And this is Oki. So Oki happened in these two because it was from 29 to 2nd of December, I guess. And this is the indicator here. Indicator network, not here. So we observe multiple peaks of susceptibility for the networks before cyclones, and susceptibility peaks are quite small for these networks which are before cyclone. We observe distinct sharp peaks and higher value of susceptibility for the networks during the cyclone. And we also observed sharp peak in the both networks of Varda because there was overlap, because the fading of Nada was coinciding with the buildup of Varda. So we observe a higher value of susceptibility for that network. The susceptibility plot shows distinct pattern before the cyclone, and we observe that the susceptibility has higher defined discontinuity and distinct range, which is greater than 50 during cyclone. So these are the so the jumps of the size. So those green lines which I was saying, these green. So these green are the quiescent period for which the jumps are of size less than 20 in the quiescent period. During the period of cyclonic activity, the jumps are higher. The dormant periods, the jump is quite less. So now this is our grid. This is, there are 10,260 grid points in that, and we have calculated the degree distribution.
The previous features of the
So these are the degree plots. This is for the canned cyclone. So this is for the first October. So network for the between for the 1st to 15 October 2016, and this is the network for the 16 to 31st of the October. And the cant was observed in this completely in this network because it started on 21 to 28th of October. So you see that the this blue line actually gives the path of the cyclone cant. It is taken from the joint typhoon warning center. This is not how this is not something we calculated, but we have plotted the and it is taken on the 6 hour interval from the 21st to 28th August, 28th October. So that's how we plotted. So we can see the degree distribution is quite different before the cyclone, and we observed so that the first figure shows the degree of each node of the before the cyclone cant, and we note that the nodes of high degree in the upper part of the graph, that is the northern part of India, near the latitude 34° north and adjacent. And during the cant,
Yeah. So first show the region.
so this is the 34 here. It was higher degree.
Pre-cyclone.
Yeah,
Right.
pre-cyclone. And
So go back. Left side network is for which period?
it is for 16 to 31st, so during the cyclone. So that
The cyclone is like
yeah.
The left
Yeah.
side.
Yeah.
That is first one.
Uh,
The left one. Left one.
yeah, this one, no?
That's the
Okay.
right one.
Yeah.
The left one is
1st to 15 of October, and this is 1st to 15 October. This is 16 to 31st October. Yeah, second part. That's how I have arranged all the plots before and during. So I will just read the line and I will show it to you that during the
path. First show where the degrees are for the cyclone and where the degrees. The nodes of high degree are before the cyclone.
nodes of high degree are before the cyclone or in this region, and that region is around 34 north and adjacent. So 34 north and adjacent. Yeah, it's the Himalayan region. And
What are the values that bar? The bar
yeah, the 700, these are quite high. And the nodes are, higher degree nodes are observed during the cyclone in this region, where the cyclonic activity was taking place, and the bar is around 600, which is not that high. The loads have shifted.
the nodes of high and the values of the high. And in fact, you can indicate the path.
But you seem to be picking two plots, right? One of the incident and then one before, right? I would have liked to see a transition, how this goes over several periods.
Yeah.
You cannot know how much computation.
Yeah, it is computationally quite extensive. We are thinking about doing.
They are actually achieving this with minimum. Okay, so go back. Here we are doing nothing special. What are we doing? We are just taking first 50 days of the month and next 50 days of the month. It's very easy to do. It is even more easy to automate. Okay. There itself you see something, and there itself you see quite good indicator. If we actually did continuous things and so on, you show where the path that we plotted it, it's very small.
Blue line, this blue line shows the path. You can, in next line, I guess.
Where is the actual path of the cycle?
Actual path of
See,
the
that
cycle.
comes from satellite picture. Satellite picture is taken at every 6 hours.
Yeah.
And it is only taken during the cycle. So
Yeah.
that is what you see
6
in
hours.
the 21st to 20th, 20.
1st to 20th of October.
Right. So when the cyclone is really active. And it's a
6
picture
hours
taken
into.
every South. So once you start seeing the clouds all over the place, I mean, you don't need all this. But you are seeing indicators much enough.
So, but you're doing this 15 days in advance. Was that ad hoc? How did they come up with 15 days? Why not 10 or 20?
I came up with 15 days off the top of my head.
But it's ad hoc. There's no.
Yeah, depending on the activity, because yeah.
See, it's not completely ad hoc. The cyclone lasts for 7 days,
Huh.
twice the period.
Yeah, twice the
This
period.
is twice the period. Second thing is, see, three parameters need to be set carefully. We set them ad hoc, and what we said was
Tau.
what size networks, how many days. 15 was simply twice of 2 weeks. Then where are we going to take the net? Because the data is available all over the world. Essentially, it's a region which including the left side of most of these are cyclones in the Bay of Bengal. There are cyclones in the one cyclone which is
Asoba.
the Bay of Bengal. Right. So there had to be a region which covers all. There are in fact dust storms over. There are even cyclones in the Gulf of Arabia or whatever it's called. You know that Gulf of Oman, etc. There are in fact dust storms there. And this entire area actually is quite important. And choosing this area has proved to be enough. We also took a much higher grid resolution. The size of the vortex.
So
So you don't need, I mean, you need higher resolution. You can't use the kind of resolution we much. Yeah, that's much smaller. I mean, size is much higher. Less like, and how the nodes of high degree are shifting, and that very
yeah, in this also you can see that
stronger than the delta I.
yeah. So this is again 15 days network during the cyclone Oki. This is 1st to 15 December, and this is 16 to 30th November. Uh, uh, yeah, so November 2nd. So you can see the degree distribution is quite different for the before cyclone, and during the cyclone you see that the distribution is quite different. It is localized in the more southern part in this region, and you also observe the highly strong, highly uh, node nodes with the higher degrees in this region, which is Himalayan region again. This Himalayan region. So that is quite consistent. So nodes of the very high degree are seen in the network of Himalayan latitude as well as in the region between 18 north and 22 north. That is in this area, and during the 1st to 15 December, these nodes shift to south close to the path of cyclone, and this cyclone kind of weeds its way towards the in the Indian Peninsula. We saw the nodes with the degrees between 800 to 1200 in the latitude band between this 12 to 16 north. This 12 to 16 north, we see higher degrees, and where we see the cyclone was actually at its peak and it veered. So that track veers inland towards 18° north. So this is the what we can say the summary or the table For the El Nino, we could get a distinct precursors and we could actually predict. But here we got the distinct feature, but still we need more data, more data points to actually construct a threshold and predict a cyclone. But we observe distinctive features and we observe certain measures which are different during the cyclone and before the cyclone, and the node degree distribution. The areas are quite different. The total number of links is quite different. So this is summarized in this. The sustained wind speed of each cyclone is mentioned. Suba is in the Arabian Sea, and so we have enlisted the value of delta chi, the node degrees, and the CC values. Yeah, so that's the. Yeah, that part I haven't included for the El Nino. That both I haven't included.
You can just explain, spend 1 minute explaining what the mic is.
As I said that the susceptibility, it's not included in the, but I can show you. Yeah. Yeah, I will show you the one. Wait. Yeah, I know. I know. No, I know. Yeah. Yeah, I'm going there. It's just taking some time. Yeah. Yeah, I'm pressing map. One second. Susceptibility and S1 plots, I'm going to show that. So that why, yeah, this. So see, the pattern is quite different. So we have done the micro transition analysis of the susceptibility pattern, and we actually tried to predict at what CC the jump will take place, depending on the jumps in the susceptibility and at what intervals it is happening. So that is the micro transition analysis, which I have not included. We have done it for both El Nino and cyclones also, but here since the pattern is quite distinct of the susceptibility, so we have tried to quantize this pattern by doing the micro transition analysis and to actually predict the percolation correlation strength CC. So that was the whole talk. Yeah, they show scaling behavior.
And the exponent, etc., I think depends on the actual year, the actual data, the actual. But there are two kinds of scaling which we see, both in the cyclone and both in the El Nino. And they are different kinds of scaling. All that
So these are the published papers and these are the references which we have used, and the end. Thank you. Thank you. Any questions? There are papers, I guess, yeah, correlation network in which they have used the mutual information, but we haven't used that thing. But yeah, there are papers and.
Essentially the same. See, this stuff is very easy. I mean, the sense, as long as you use any kind of correlations, it is my belief that you will get the same. Okay. If you start using something like a recurrence, it will simply not work.
Yeah.
Yeah, it will just not give any result.
Yeah.
But I think correlations, whether you use this definition.
No, but yeah, actually you can. Yeah. Yeah, that's what he was talking. Udit Bhatia, I talked with him regarding. So he said you can use a vertical column in which you can see the more fluctuations, and that will be more beneficial to use the pressure gradient as a instead of using the temperature. But here also we got certain distinct features.